Okay, so let's start the session. Hello, everyone. Welcome to our second session on the James Webb Space Telescope, named Exploring the Unknown, organized by SEDS-VIT, the Students for the Exploration and Development of Space. Today, we are joined by Dr. Matthew Greenhouse. He has served on the James Webb Space Telescope senior staff as the project scientist for the Webb Science Instrument Payload since 1997. He specializes in infrared imaging spectroscopy, development of related instrumentation and technologies, flight project science, and technical management. So, without any further ado, I hand it over to you, Dr. Greenhouse.
Okay, well, thank you very much, everyone, for tuning in to learn about the James Webb Space Telescope. Stand by. Space telescopes are our most powerful tools for looking back in time. Traveling back in time is the stuff of science fiction, but looking back in time is something that we can actually do. And it's made possible by the finite speed of light. If you look at someone who might be in the room with you right now, you're not seeing them as they are. You're seeing them as they were a few nanoseconds ago. That is because it takes light a few nanoseconds to travel a distance of 1 meter. Now, a nanosecond is a really small amount of time. So that transmission delay is imperceptible to us in our everyday lives. But as we look at objects that are farther away, the effect becomes more pronounced. For example, if we had a magic switch that could turn off the sun and we flipped that switch, it would be 500 seconds before we saw anything happen. That's because it takes 500 seconds for light to travel from the sun to the earth. And so when we look at the sun, we're not seeing it as it is, we're seeing it as it was 500 seconds ago. If we look at the closest star, we're seeing it as it was 4 years ago. If we look at the center of our galaxy, we're seeing it as it was 25,000 years ago, and so forth. And so with telescopes, particularly telescopes in space, we can look back in time to explore the universe. And that is very much what the JWST is designed to do. Now, the mission was conceived in the late 1990s to relate this famous image taken by NASA's COBE satellite. It is an image of the universe when the universe was a few 100,000 years old. And it records the moment in the evolution of the universe shown on this cartoon when the universe became transparent and light could escape. These blobs of color denote temperature inhomogeneities that are the seeds from which galaxies will eventually form. Now, at about the same time, the Hubble Space Telescope recorded its deepest image that Hubble was capable of taking. And that image shows the universe when it was about 1 billion years old. And between the epoch that COBE observed and the epoch that the Hubble Deep Field observed is a somewhat mysterious, poorly studied epoch known as the cosmic dark zone. And it's of great scientific interest because that is the period in the evolution of the universe when the first stars and galaxies formed, when the universe was about 100 million years old. And the reason it's poorly studied is that we haven't had the right type of telescope in space to study it. And so the JWST was designed to fill that gap. And as we'll discuss, it does lots of other science, but that was one of its key mission objectives. Now, when the Hubble took that famous image, it did so by staring at a single spot on the sky for a very long time, a couple of weeks, leaving the camera shutter open, if you will, metaphorically. And this is what that image looked like. And nearly everything in this image is a galaxy. So although we looked back in time as far as Hubble is capable, there is still a lot more to see in this image. The image is still filled with galaxies. Now, when the JWST repeats this experiment, it will do it much the same way. It will stare at a single spot in the sky for a very, very long time. But because the JWST has a much greater light gathering capacity than the Hubble Space Telescope, it has a much bigger primary mirror. And because it operates in the infrared spectrum, it can look all the way back to the epoch of galaxy formation, so that there would be nothing left to see in terms of galaxies. When we say that the James Webb Space Telescope will see the first galaxies, we don't mean that you will pick up a copy of the newspaper and see a picture of the first galaxy. What we mean is that the JWST will study the star formation rate per unit volume in the universe as a function of look-back time, or redshift. And this is what we know today. And you can see that as we go to high redshift, a great look-back time, the errors on these data get bigger, and the data stop. And JWST will fill in this portion of the curve with high signal-to-noise data, so that we will see the formation epoch, and we will actually be able to discriminate between various theoretical models of how the universe evolves. Now, this running in the lower left here is a supercomputer simulation of the formation of the universe. And as one can see here, the normal matter in the universe, the matter that we can see, is distributed in a spider web type arrangement known as the cosmic web. And the JWST will help us understand how this structure evolved over the history of the universe. When we look at galaxies nearby, we see them appear as you've seen in pictures in textbooks. They are very symmetric objects. Some have spiral arms, some have bulges, but they have very symmetric shapes or morphologies, as we say. However, when we look as far back in time as Hubble can see, the shapes of the galaxies or their morphologies actually change, actually look different. They, instead of being these very beautiful symmetric objects, as we look back to when the universe was young, they appear very irregular. And the JWST will help us understand what gives rise to that evolution of galaxy morphologies. We do see irregular galaxies nearby. These are Hubble pictures of irregular galaxies. And we believe that these morphologies result from collisions between galaxies. This is a computer simulation of galaxies colliding. And with simulations like this, we're actually able to reproduce some of the irregular morphologies that we observe. And we believe that this is the process that causes the primeval galaxies to look different. In the early universe, collisions between galaxies were more common, believed to be more common than they are today. So the Webb will help us understand that process as well. Now, you've all heard the statement that space is expanding. What do we mean by that? Well, this analogy is a good way to understand what we mean. Here we have a loaf of raisin bread dough that's been set out to rise. And imagine that you are seated on one of the raisins. What would you see? you would see all the other raisins moving away from you, even though you are not at the center of the expansion. And no matter what raisin you chose to sit on, you would see exactly the same thing. So that is very much a good analogy for what we believe we have in the universe. When we say that space is expanding, we don't mean that objects are flying through space as if they, as the result of some explosion, but rather the space itself is expanding, just as the raisin bread dough is expanding here. Now, why is that important for the JWST? Well, when we look at these primeval galaxies, the first galaxies to form, the light that they produce is produced in the ultraviolet part of the spectrum. But as that light travels to us through the expanding space, through that expanding raisin bread dough, its wavelength is stretched into the infrared part of the spectrum. So to see those galaxies today, we have to build an infrared telescope. Now, the capability that we put into the JWST to observe in the infrared is crucial to seeing those first galaxies, but it also enables a wide range of other science that the JWST will do. So what do we mean by the infrared spectrum? Light comes in an infinite spectrum of wavelengths, from infinitely short to infinitely long. But our eyes are only sensitive to a very narrow range of wavelengths. This is the range of wavelengths that can pass through the Earth's atmosphere and reach the surface. So our eyes have evolved to see this narrow range that we call the visible light range. The Hubble Space Telescope was designed to observe in the visible and ultraviolet part of the spectrum, whereas the JWST is designed to observe in the red edge of the visible out into the mid-infrared spectrum for reasons that we've discussed. Now, our eyes cannot see this infrared light, but our skin can feel the infrared light. If you hold your hand near a stove burner or a radiator, the heat that you feel on your hand, your skin is actually sensing the infrared light. Okay, so this is a famous picture of the Eagle Nebula. The spaces between the stars, the so-called interstellar space in our galaxy, it's not a cold, empty vacuum. It's filled with clouds of molecular gas and dust and plasma and all kinds of things. And when the Hubble Space Telescope looked at a portion of the Eagle Nebula shown here, it took what has become a very called the pillars of creation. And what we have here are, these are filaments of a giant molecular cloud of gas. And there is dust mixed in with that gas, which is making it appear opaque. Now, if we look at that same exact field in the infrared, one can see that the longer wavelength infrared light can penetrate the dust and allow us to see what's going on inside the cloud. And this will be crucial for our ability to study star formation in our own galaxy. We know the basics of star formation. We know that these giant clouds of molecular gas are the birthplaces of stars. The clouds collapse onto themselves by self-gravity. And as those clouds collapse, the pressure inside the cloud becomes very high. And so the temperature becomes very high. It's not unlike what occurs when you fill your bicycle tire at the gas station. When you fill the tire, it gets a little bit warm. The same thing happens inside these clouds, only in this case, the temperature gets really, really hot. to the point where nuclear fusion can occur, and then the star is born. JWST will help us understand, further understand how stars form and evolve. And one aspect that's very important for JWST is to study circumstellar disks. When a star is formed, there is typically a disk of material that surrounds the star left over from the star formation. And those circumstellar disks are of great scientific interest because they are the birthplaces of planetary systems like our own. And there are lots of ways that we can observe those planetary systems. One way is shown in this computer simulation. As the circumstellar disk evolves and when planets form, the planets sweep up gas and dust from the disk to produce this sculpted disk arrangement. And we've actually observed these sculpted disks using a giant radio telescope in Chile. And so this is real data. This is not a simulation. And JWST will do a lot of work on circumstellar disks to understand how planetary systems form and evolve. This is an artist's rendition of the debris disk surrounding our own star, the sun, alongside a map of where this debris actually exists. These are the so-called Kuiper belt objects or trans-Newtonian objects, and they are of great scientific interest because these are chunks of material, primordial material, left over from the formation of our solar system. And we've just recently, for the first time, actually visited one of these chunks of material, a Kuiper belt object. The New Horizons mission that was sent to fly by Pluto, after the Pluto part of the mission was over, we sent it on to obtain this first image of a Kuiper belt object. And this is what it found. That object turned out to be two smaller objects stuck together. And that's of great interest for planet formation theory, by which planets form by agglomeration of small particles into successively larger particles, ultimately forming a planet over 100 million years or so. And computer simulations of this Kuiper belt object have shown that a very low velocity collision, just a few kilometers per second, can cause two bodies to fuse like this without either one being destroyed in the process. So we have put special non-sidereal tracking capability into the JWST to allow it to observe these objects and the planets of our own solar system. Now, JWST will do a lot of work on the planets of our solar system. For example, JWST will observe the Great Red Spot on Jupiter. This is a storm that's been raging on Jupiter for more than 400 years. We see today that it's shrinking, and JWST will help us understand or help us explore why the Great Red Spot is shrinking and why it's red. We still don't know why the Great Red Spot is red. The Webb will search for small moons of Saturn that were too small for flyby spacecraft to see. And JWST will study water in our solar system. Most of the water in the solar system may not be on the Earth. Moons of Jupiter, Europa, and Enceladus, a moon of Saturn, are believed to contain vast oceans that are enclosed by a crust of ice. Tidal forces acting on that ice cause it to crack, producing geysers of ejecta that are erupting through the ice. And here in the lower right is a Cassini spacecraft image of this process occurring on Enceladus. JWST will study these ejecta spectroscopically to measure their chemistry and understand, thereby explore these oceans that are underneath the ice by studying the ejecta that we can see. Now, today we know that all stars have planets, practically speaking. We've discovered nearly 5,000 exoplanets, as they're called, planets that are orbiting stars other than their own. And therefore, we know that there are tens of billions of habitable worlds in our galaxy. We don't know that they're inhabited, but we know that those habitable worlds exist. And most exciting, we have learned how to search for life on them by studying their atmospheres. And so the search for extraterrestrial life is no longer the stuff of science fiction. In fact, it's a major science objective of NASA. So how can we search for life on an exoplanet that is so far away we can barely see it? Well, the key is a process known as spectroscopy. And in spectroscopy, we spread light out into its component colors so that we can see the emission and absorption of individual atoms and molecules in the gas. Here we have spectra of Mars, Earth, and Venus. So what is a spectra? Spectra is a plot of brightness on the y-axis and wavelength on the x-axis. And you can see that there are lots of bumps and wiggles in this spectra of the Earth, for example. If the Earth had no atmosphere, this would just be a flat line. All these bumps and wiggles are due to emission and absorption of atoms and molecules in the atmosphere of the Earth. And we can actually identify which atoms and molecules are producing each of these features. And so with spectroscopy, we can measure the chemical composition of the atmospheres of exoplanets. And in particular, we'll be looking for chemistry that would not be expected absent biological processes. You know, for example, the Earth has much more oxygen in its atmosphere than it would have if there were no life on Earth. So how can we obtain these spectra? One way that that the JWST will use is something called transit spectroscopy. And the process is shown in this cartoon. Imagine that we are observing some exosolar system, some alien solar system, such that the planets are orbiting along our line of sight to the star. And imagine that a planet wanders into our line of sight when we're looking at that star, and we take a spectrum. What do we see? We're going to see the spectrum of the star and the spectrum of the planet's atmosphere. Now, if we just wait a little while for the planet to move out of its way, then we'll take the spectrum again, and we will subtract the two, and voila, we have a spectrum of the exoplanet's atmosphere. And this process has developed into an exact science using the Hubble Space Telescope and other facilities. And JWST will do a lot of this work. JWST can detect water vapor on an exoplanet that is just a few times the size of the Earth. You know, why do we care about water in searching for extraterrestrial life? It's not because alien life might get thirsty and need something to drink, but rather for the organic chemistry of life to occur on a planetary scale, one needs a liquid solvent available on a planetary scale, and water is what we're most familiar with. Okay, so when we first put pencil to paper on what type of observatory we had to build to do all that science, we determined that we needed 7 times the light gathering capacity of the Hubble Space Telescope to see those primeval galaxies, which are very faint. And we also determined that we needed Hubble's ability to see fine detail, angular resolution, as they call it. But we needed that in the infrared spectrum. So it turns out that also requires a very big mirror. And as we mentioned, we needed to build an infrared telescope to see the light from those primeval galaxies. And when we realized those 3 things, we also realized we had 2 big problems that that we needed turned out to be larger in diameter than the biggest rocket. That was problem number 1. Problem number 2 was to build an infrared telescope. The telescope has to be made very, very cold. And this is because anything above absolute zero emits infrared light. So if you had infrared glasses on, you would see your body glowing in the infrared. The walls and floor of the room would be glowing in the infrared. And if we didn't make the Webb telescope very, very cold, it would be blinded by its own infrared emission. And it turned out that we had to make it really, really cold, minus 200 Celsius. And there was no, even today, there is no mechanical refrigerator that could cool something as big as the JWST to such a low temperature. And so these were 2 problems that we had to solve. And fortunately, we did solve them. Let's talk about the cooling problem first. The JWST will not be placed in orbit about the Earth the way the Hubble Space Telescope is. We will send it to a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful. We just call it the L2 point for short. And this point in space is about 1 million miles away from the Earth in the anti-sun direction. And what is there's a number of things that are special about this L2 point. But one is that when we are at the L2 point, all the sources of heat on the JW moon always lie in the same direction. As the Earth orbits the sun, this pattern of Lagrange points orbits with it. So we realized that if we deploy a giant sun shield to block the heat from the sun, Earth, and the moon, so that the telescope would always live in the shadow of its sun shield, then the JWST can cool passively by just radiating its heat energy away to the cold darkness of space. And we had to size that sun shield so that the JWST could observe the whole sky and still remain in the shadow of the sun shield. So we sized the sun shield so that the JWST could point 5 degrees toward the sun, and it's still in the shadow, and 45 degrees away from the sun, and it's still in the shadow. So now we've observed an arc on the sky 50 degrees long. And now you can see that if we rotate the JWST about the Earth-Sun line, that doesn't spoil our shadow situation at all. And so now this arc turns into an annulus that covers 35% of the sky. So at any moment in time, JWST can point at 35% of the sky and still be in the shadow of its sun shield. Now, as the Earth orbits the sun, we're rotating about this axis. And so every 6 months, this annulus sweeps over the whole sky. So every 6 months, JWST can observe any point in the sky and still be in the shadow of its sun shield. So that's how we solve very large. It's the size of a tennis court. We'll talk a little bit more about that in a moment. The other thing that is special about the Sun-Earth Lagrange point, L2, is that as the Earth orbits the Sun, the L2 point, of course, follows the Earth around the Sun. And so the telecommunications range between the JWST and the Earth, the distance between the JWST and the Earth, remains constant over the whole mission, no matter how long the mission lasts. And that's very important to getting the data back. The JWST will not be exactly at the L2 point, but rather we're going to put it is in a small orbit about the L2 point. And that is to ensure that the JWST stays out of the Earth's shadow. On JWST, we are generating electricity with solar arrays. It takes about 2 kilowatts of power to run the Webb. And so it's important that we stay out of the Earth's shadow. That orbit about the L2 point is unstable. It needs to be maintained by station-keeping thrusters. And the propellant for that, to maintain that orbit, we now know will last about 20 years. So as a consequence of that, it is unlikely that propellant will be the life-limiting factor of the JWST mission. So this little video shows how JWST orbits the L2 point as it's also orbiting the Sun. Okay, so how did we solve the giant mirror problem being bigger than the largest rocket fairing? We adopted something called a segmented mirror architecture. In this approach, rather than building one giant mirror, we built a mirror that is composed of 18 hexagonal segments that are mechanized such that they can play together as if they were part of a single mirror. And that allowed us to fold the JWST up inside the rocket fairing. The JWST was designed to integrate with a French rocket called the Ariane 5. It uses a 5-meter diameter fairing. It was launched from Kourou Launch Center, which is in French Guiana on the east coast of South America. The payload is about 6.5 metric tons. And the unfolding of the JWST that you'll see in a moment involved 40 deployable structures and 178 release mechanisms, every one of which had to work perfectly. The JWST is much too far away for it to be serviced by astronauts. And so it was absolutely critical that all of these mechanisms worked perfectly, and they did. But this animation shows that process. The first thing that you see happening is the solar array comes out so that we can become power positive. We're operating on batteries up to this point. And next, the high gain antenna comes out so that we can begin communicating with the JWST. There are some rocket firings that occur to get us on course to the L2 point. And what you see happening here are giant pallet structures are deploying, and inside those pallet structures is folded up that tennis court size sun shield. A deployable mast extends to separate what will be a very cold telescope from what must remain a room temperature spacecraft. And now you see these telescopic booms coming out that are pulling the sun shield out of those pallet structures. And then these devices on the periphery of the sun shield spread it into its 5 layers that are needed to give it the thermal performance that we require. Various other smaller radiators deploy, and soon you will see the secondary mirror of the telescope deploy. So there goes the secondary mirror. And now you will see the wings of the primary mirror deploy much like a round drop leaf kitchen table. And all of this happened successfully not that long ago. All right, the JWST telescope mirrors are not made of glass, as most telescope mirrors are. They're made of a material called beryllium. And the reason that we chose beryllium is that as the telescope points in various directions around the sky, there will be thermal gradients that form in the primary mirror. And so we had to find a material that had a low coefficient of thermal expansion at that minus 200 Celsius operating temperature so that those thermal gradients would not spoil the shape of the mirror. And it turned out that beryllium has that property. And so the beryllium starts out in a powder form, and we compress it under great heat and pressure into a block of material called a billet. And then after going through all the trouble to do that, we machine away almost all the beryllium that's there. So this is what the back side of a JWST mirror segment looks like. And this is the front side, the shiny side. What you see here is lab equipment reflected in the mirror. For anything that flies, whether it's an aircraft or a spacecraft, weight is really a premium. And so the figure of merit here for these mirror segments is areal density, mass per unit area. And the JWST mirror segments are about 6 times lighter than the Hubble mirror, and they represent the current state of art for lightweight mirror segments for space telescopes. Now, if you're thinking ahead, you'll realize that we have another big problem that we have to solve. How do we polish telescope mirrors? Well, we rub on them with gritty stuff until they get smooth and shiny enough. And that polishing is a room temperature process. So if we're going to polish a mirror at room temperature and then use it at minus 200 Celsius, that means that we have to put in the wrong shape at room temperature in order to get the right shape at the operating temperature. This is done through the magic of computer modeling, but computer modeling is not perfect. And so we had to follow an iterative process whereby we would polish the mirror segments partway, and then we put them in a specially instrumented space simulation chamber at Marshall Space Flight Center near Huntsville, Alabama, where we could cool the mirror segments to their operating temperature, observe them with special optics test equipment to see how our model is tracking to reality. And then we would make adjustments to the model, do some more polishing, and we would iterate that process. And the result is shown here. It was very successful. This is a typical picture of a JWST mirror segment at room temperature. These colors denote relief, like topographic relief, if you will. And when we cool that to the operating temperature, the mirror becomes completely flat. And so this was a lot of work to make these mirror segments. Of course, it was that work is behind us now, and it was done successfully. But it's one of the reasons why it took so long to build the JWST. All right, this is a robotic pick-and-place machine in a clean room at Goddard Space Flight Center. And what you see happening here is those mirror segments are being integrated to the structure that holds them, the backplane structure. These are the actual flight mirror segments. They look black because they have covers on them to keep them clean. And this machine has a robotic arm with a very high precision end effector or tool on the end of it that is helping the technicians get those mirror segments integrated to the structure in exactly the right place. You get the idea. Now, these mirror segments, they are mechanized in 7 degrees of freedom, the 6 that you're familiar with, plus radius of curvature. And that is crucial to enabling them to play together as if they were pieces of a single mirror. They have to be aligned to a small fraction of the wavelength of light by those mechanisms. And we do this with special interferometric optics that is in one of the science instruments for this purpose. And when we first look at a star with the JWST, which we recently did, what we have is 18 telescopes. So we see 18 separate images of that star. And then we use those mechanisms to combine those 18 images into a nearly perfect single image. And that is what is happening on the JWST as we speak. This is not a simulation. This is the first image of those 18 images. So this is an image of a single star that you're seeing 18 times through each of the 18 mirror segments. And right now, today, we are in the process, having achieved this, we are in the process of combining these images into that single perfect image. One of the instruments on the JWST has the ability to image the primary mirror rather than the sky to help us with this process. And this is an actual picture of the JWST primary mirror taken not that long ago in flight. All right, let's talk a little bit about that sun shield. The JWST sun shield has an SPF of more than 1 million. So if you had this on the beach, you would be very well protected from the sun. It is literally the size of a tennis court, 73 by 40 feet. And it has 5 layers to give it that SPF of 1 million. Each layer is made of a heat-resistant plastic-like substance called Kapton. Each layer is thinner than a human hair. The sun-facing layer is coated with silicon, so it actually looks pink in reality. And the remaining surfaces are coated with aluminum. And the sun shield is a very special curved shape that gives it its thermal performance, and also is important for ensuring that stray light doesn't reflect off of the sun shield and get into the telescope. Those of you who sew may realize that in order to get a curved shape out of flat cloth, one has to have lots of seams. And so each layer of the JWST sun shield is a quilt of about 50 pieces. And in this case, the seams are not made with needle and thread, but rather with thermal spot welds. There's about 7,000 inches of thermal spot weld seaming that has to be super duper precise. And so this sun shield was itself a major engineering achievement. And it was one of the higher risk areas of the whole JWST mission. That risk is now retired. All of the deployments that you saw in the animation have occurred successfully. All right, this is a deployment test of that sun shield. Here you see the sun shield folded up in those pallet structures that you saw in the video. Those mid booms are pulling it out of the pallet structure. These plastic tables are there to provide gravity offloading. Of course, they're not there in space. But this is an example of just some of the testing that we had to do to design the sun shield deployment. You'll notice there's a person appearing in the middle here. That gives you a sense of scale. This is a truly enormous sun shield. If you look closely, you can see the seaming. And this is just an example of what this sort of work actually looks like. This is occurring in a clean room at Northrop Grumman Aerospace Systems in California. Okay, let's talk about the science instruments that are on the back side of that primary mirror. And they are the instruments that actually do the science. The main infrared camera is shown here. It is the instrument that will take the first images of those primeval galaxies. It was made in the US, led by the University of Arizona and with their contractor, Lockheed Martin Advanced Technology Center in Palo Alto, California. This is the main spectrometer on the JWST. It was developed as a partnership between the European Space Agency and Goddard Space Flight Center. And it's a very unusual spectrometer in that it is something called a multi-object spectrometer. It is designed to record spectra of 100 targets simultaneously while keeping those spectra separate. And that was a crucial capability for the JWST because those faint, those primeval galaxies are very faint. So if we had to study them one at a time, we would not be able to get a large enough sample size within the lifetime of the JWST. So we had to develop technology that would give the spectrometer this multi-object capability. This is the mid-infrared instrument on the JWST. This is the instrument that will observe farthest into the infrared. It has imaging and spectroscopy capability. And this is the instrument that will give humanity its first high-definition view of the infrared universe. We will be able to see the infrared universe in the same detail as the Hubble Space Telescope has shown us the optical universe. And this instrument was produced by a consortium of 10 European countries along with NASA's Jet Propulsion Laboratory. And finally, this is the Canadian Space Agency Fine Guidance Sensor, which is also a science instrument. The fine guidance sensor part can sense pointing to a millionth of a degree, or about 3 milliarc seconds. So this is the device that allows us to get the JWST pointed at the objects of interest. And it also has a science instrument function that is very much focused on obtaining those exoplanet atmosphere spectra. Okay, after we got those science instruments integrated to the telescope, then we put that telescope in its folded up configuration and into a specially designed shipping container that preserves it in the super clean, super dry atmosphere that's necessary to keep it qualified to fly in space. And we loaded that into a C-5 transport aircraft. It just barely fit in there, as you can tell, but we did get it in there, and we flew it from Andrews Air Force Base near Washington, D.C. to Houston, Texas, to do some more testing at the Johnson Space Flight Center near Houston, Texas. There, we did something called an end-to-end optical test. And the mental image that you get when I say end-to-end optical test is exactly the right image. We are going to put the JWST into this giant space simulation chamber, shine light through the whole system in the same way that it will occur on orbit, and make sure everything is working properly. This is a test that we did not do on the Hubble Space Telescope program, with consequences that you're probably aware of. It's a very expensive, difficult test, but we elected not to skip it on the JWST, and it's a good thing that we didn't, because we did find some problems in this test. In order to do it, we had to bring into service the largest cryogenic space simulation chamber in the world. It is left over from NASA's Apollo program. It's called Chamber A. And here you can see the Apollo command module in that chamber, looking through the chamber door. We refurbished that chamber and rolled the JWST into it on rails. We were able to suspend the JWST on rods from the top of the chamber and shine light through it and observe the result with special optics test equipment. And in order to do that test, and that test was done, and it was an important test for the JWST. Now, after we finished that test, we went back into the aircraft, and this time we flew to Los Angeles, California, so that our contractor, Northrop Grumman Aerospace Systems in Redondo Beach, California, could integrate the spacecraft and the sun shield elements to the telescope with its instruments. So let's take a look at what that process looked like. This is the telescope in its stowed configuration. Here is the sun shield folded up in its pallet. The spacecraft is underneath the sun shield, so you really can't get a good view of that. But here we're integrating the telescope assembly to the sun shield and spacecraft assembly. Now, of course, after we integrate it, we have to test it to make sure that everything is working. And after we do that, we have to do two key tests. One is that we have to subject this whole assembly to the vibration that it will experience during the rocket flight to space. And then we also had to put it in an acoustic chamber and blast it with sound from giant loudspeakers to simulate the acoustic energy that it would be exposed to in the rocket flight to space. And then after doing that, of course, we had to test it to make sure that we really did pass the test. So all that work was completed. And then now that we've added the sun shield in the spacecraft, we can no longer fit in the aircraft. And so instead, we put our special transport container, now a little bit bigger, into a special roll-on, roll-off transport ship. And we shipped from on that ship, we traveled from Los Angeles, California, through the Panama Canal to French Guiana. It's the first time that NASA has shipped a payload by ship. And that was all completed. And here we are in the launch facility in French Guiana. And here we have the last glimpse of the JWST on Earth. What's happening here is the JWST folded up has been attached to the rocket right here. And they are lowering the rocket fairing, or nose cone, as you might call it, down onto the observatory to get it ready for launch. And the Webb was launched on Christmas Day successfully.
Turbo pumps will come up to flight speed for 7 seconds, and the command will be issued to ignite the solid rocket boosters. The James Webb Space Telescope will be on its way. T-minus 30 seconds and counting. Standing by for terminal count.
So this was a nail-biting moment for everyone involved.
9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
Okay. So the rocket launch was very, very successful.
Earlier, the Vulcan 2 engine will ignite.
And as a consequence of that, we had to use much less than the expected amount of fuel to navigate to the L2 point. And so we have plenty of fuel on board to do the Webb telescope mission. And so we're confident at this point that propellant will not be the life-limiting factor on the JWST. Now, here we are in the timeline. So we are in the process of commissioning the telescope. Right now, today, we are combining those 18 images into the one perfect image. And that process will continue for about another 60 days. We have to get the telescope tuned up exactly to support all of the science instrumentation. All of the 4 science instruments are powered on and working, and the whole observatory is coming to thermal equilibrium. You can really follow the action of every little achievement along this timeline by going to our blog site. Every time we achieve something, we put out a blog post on it. And this whole commissioning period is about 6 months long and will end in a June timeframe. And that's when the science observations will begin. So let's just recap.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sun shield ever flown. A 5-layer, tennis court-sized sun shield that blocks heat from the sun, Earth, and moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
Okay, so how does the universe work? What's our cosmic destiny? What will be the future of the universe? And are we alone? These are the questions that drive NASA astrophysics. The Webb will contribute to humanity's quest for answers to those questions. And you can join the quest. The scientists and engineers and managers that build projects like this come from all walks of life, all backgrounds. Every type of engineering that exists is employed on big space projects like this. And you can join them. You can aspire to go into aerospace engineering as a career goal, or astrophysics, if you like, and join projects like this. There's a quote that I like to read. The book of nature lies continuously open before our eyes, but it cannot be understood without first learning to understand the language and characters in which it is written. It is written in mathematical language, and its characters are geometrical figures. That's as true today as it was 400 years ago when Galileo said it. So to go into this kind of work as a career objective, go to college. If you're already there, stay there and study whatever you love. But science, engineering, and math often apply to this sort of work. And consider this as something to do with your life. Can be very rewarding, fun, and exciting. Okay, so that's my remarks for today. The mission is going great. Everything is working to this point, and you can follow the progress on our website and on our blog post. And I'll be happy to answer questions for as long as you have them.
Thank you so much, sir. So, okay, participants, if you guys have any questions or doubts, you can put it in the chat box and I will read them out. Meanwhile, we have collected a couple of questions, so I'll ask them. Why was origami used as a method to pack and fold the satellite instruments?
Okay, so the question is, why did we use origami?
Yes, sir.
Well, because there is no rocket big enough to hold the JWST when it is not folded up. The mirror is about 6.5 meters in diameter, but the largest rocket fairing available to us today is only 5 meters in diameter. So we had to find a way to fold up the observatory in the rocket fairing.
Okay, the next question. What is NASA's contingency plan against equipment failure, like the one that recently happened on Hubble? As planning any repair missions to the telescope would be an extremely difficult task.
Yeah, so as I mentioned, the JWST is too far away for astronauts to fix it if something doesn't work. And so we've had to address that several different ways. The JWST has much more adjustability than the Hubble had. So it's very tolerant to things that might go wrong. And we've had to do a lot more testing than we did, say, on the Hubble Space Telescope. So through a combination of testing and redundancy and adjustability, we believe we've designed a very highly reliable system. And so far, that's been borne out by the in-flight experience.
Okay, thank you, sir. So we have a question in the chat box. Abhijit wants to know, what is the measure taken to escape collisions from, say, meteors or something like that?
Well, the JWST will be hit by micrometeorites, as this is true of anything that flies in space. And so we've had to design it with that in mind. The 5 layers of the sun shield, when the sun shield is hit by a micrometeor, it only penetrates 1 layer. And so we had to design the JWST for all the aspects of the environment that it will experience at the Sun-Earth L2 point. Micrometeors are one example of that. Radiation is another example. And so that's part of the challenge of designing spacecraft, is the environment that they operate in is quite different than what we have on the surface of the Earth.
Okay, so the next one. So in layman terms, what sort of contaminations or disturbances could you face when gathering data coming from or coming up with observations?
Well, let's see, contamination. One thing that we have to be very concerned about is formation of ice on the telescope optics. Ice is black in the infrared, so it's important that as we cool the JWST down, and it's very cold now, we've had to cool it down in a very careful way to make sure that no ice forms on the optics. And we appears to have done that successfully. We have means of sensitively measuring whether any ice is accumulating, and thus far we have not seen any. But that was one contamination aspect that we had to carefully engineer for.
Thank you, sir. First of all, thanks for this thought-provoking and mind-blowing presentation. I have a question regarding the sun shield. Is that the sun shield already reduces the temperature to like minus 233 degrees. So, but then when I was looking and reading up on the JWST, I heard there are also cryocoolers put in position for the MIRI and NIRCam's operation. So my question is, weren't the sun shields enough to cool it down to a certain degree that we even need a cryocooler? Like, do we need cryocoolers, or like what role do the cryocoolers play?
For all the instruments except the MIRI, we don't need cryocoolers. But the MIRI instrument that observes farthest into the infrared, its detectors have to operate at about 6 degrees above absolute zero. The rest of the observatory is running between 40 and 50 degrees Kelvin. But the MIRI detectors have to be colder than that. And so one of the challenges was that we had to develop a cryocooler to give the MIRI that little extra bit of cooling to get from 40 Kelvin to 6 Kelvin. And that cryocooler had to accommodate all of this origami that you saw. And so there is one cryocooler on the JWST, and we're just beginning to turn it on now, but so far everything is working well. And yeah, so that's the answer to your question, I think.
And one more question from me is that I read upon the Curiosity and Perseverance rovers and how they use this radiothermoelectric generators. But then in JWST, could we have used an RTG so that we could have compensated the weight of the sun shield and placed JWST in such a position that we don't need to worry about the sun because the RTG is powering everything? Could we have done that?
Not really. We could generate electricity with an RTG device, but it's much simpler to use solar arrays when solar arrays are practical. If we're going to the outer solar system, a mission like Pluto, we're too far from the sun to use solar arrays, and that's when we use the RTGs. But for JWST, the solar arrays are the simplest, most practical solution.
Thank you, sir.
Okay, so one more final question. James Webb Telescope is a marvel of engineering, and a lot of innovation has been done to achieve this. Has the JWST provided us with any technology that can be implemented here on Earth?
Oh, quite a bit. We call them spin-offs when NASA technology gets used for other things having nothing to do with flying in space. Some of the optics techniques that we developed for the JWST are now being used in instruments designed for surgery of the human eye. There are a list on our website of several important technology spin-offs that have occurred, and that is typical of all NASA missions. There's a pretty strong relationship between technology that affects our everyday lives and space missions like the Webb, and especially Earth observing missions, weather satellites, and so forth.
Okay, I think, thank you so much, sir. I think let's end it now. We're exceeded the time. Once again, sir, thank you so much for taking time out of your very busy schedule and making time for us and delivering this amazing and informative session.
Thank you for having me.
Thank you. And also to all the participants, especially the freshers of VIT, don't forget our recruitments are still the round 1 of SEDS-VIT recruitments is still going on. Today is the last date, so be sure to register on VTOP and attempt our round 1. All the details are there on our Instagram handle. Once again, sir, thank you for joining, and all the participants, thank you for joining us today. Hope you had a wonderful time.
Bye-bye.
Bye. Thank you.